Recently, Mark Ryan, aka Super Review, put out a video on IEM ear tips, how to use them, how different shapes affect the sound, a whole bunch of practical information based on hundreds and hundreds of IEMs he has experience with and he's reviewed over the years. He's got all of that experience. I don't have any of that. I do have, though, something he doesn't have. A whole bunch of detached human ears. This is a video about what we can actually learn from all of these to help with that fitment. My goal here isn't to actually detract from anything he said. It's a fantastic video. I really just want to amplify three different things and get at some notion as to why it is that it's such a big factor. He said in there that he's not trying to approach it from a scientific standpoint, and I am here. This is going to be hitting a couple of figures from some scientific papers. By day, I'm a researcher. I'm a neuroscience researcher. My area isn't audition or anything like that, but I do read scientific papers, well, for a living. And so what I want to try to get across here at these key points. I mean, first, your ear canal is not just a simple tube. The shape of that canal is going to impact the fitment of the IEM. It's going to impact the shape directly, but then also that fitment and shape interaction is going to actually deal with it. So its geometry interacting with the IEMs and the tips is going to dictate not just the seal that you have and not just the comfort that you have, but also then really the frequency response that you hear. That position that it sits in there, well, that's going to be varying the length of that inner ear, that ear canal, I should say, sorry, that acts as a resonator, and that for each of us is resonating at a certain frequency and a little bit different frequency, and our brain has come to expect that resonance at that frequency. And so if the IEM and ear tip is changing that, and changing it in different ways based on the ear tip and the length of the nozzle and everything you're going to use, that's going to impact the frequency response, impact the timbre of the sound that you hear. So then in all of this, one of the big things is that IEMs face a real challenge. They have to assume something about the shape of the pinna that you have here, because it's bypassing that, the concha, both of which are affecting the frequency response here, and then that ear canal, which is amplifying. Its whole point is to amplify certain frequencies inside of there so that we can do things like hear speech and everything better, and so we can localize things better. And that whole process, as you're putting an IEM in there, blocking off that canal and blocking it off at a variable kind of length and a length that it's not normally sort of expected to be, that's going to be impacting things. So let's take a look at it a little bit. Research has shown that there is a lot of variation in the shape of that canal. You can see, of course, on the outside the pinna itself and how we have that, but research has also shown that there's a significant amount of variation in that canal. So in this paper here, and you'll actually notice, by the way, B and K are actually one of the authors on this here. Here are three different individuals. And what we have on the bottom is that concha, that outer part, that sort of bowl that you see. And as it moves up and down here, this is moving closer and closer and closer to the eardrum. So what you can see on here is that there's, a different shape in that canal, in that concha that you can actually see externally. But inside, this one is far more narrower than this one, which is narrower than this one still. They all have a similar sort of bend shape to them, but the actual geometry there is quite different. And the length is actually different. They didn't just look at those three. Here are then all 45 ear canals that they'd actually scanned with MRI. And you can see across this, there's obviously a massive amount of variation. That variation in length and in shape matters in terms of the frequency response. This actually happens to be a student's master's thesis that I found on the web. And in here, what the person was doing was trying to come up with accurate ways of measuring and modeling, physically modeling the ear canal. So we can see here, and as Super had actually shown in his review, that length can impact the underlying frequency response. The ear canal acts as a quarter wave resonator, in which then the wavelength or the frequency that you're going to be getting peaks at is directly related to then the length of this. An average human is somewhere around 20 in mid-20s in terms of millimeters worth of length on all of this. And what this is showing is as you go from one length to another, you are changing then the resonance frequency. This is 1 kilohertz, 2 kilohertz, 3 kilohertz, 4 kilohertz. This is part of that whole ear gain that everybody talks about. But as you can see, we're moving from just over 2.1 kilohertz or so as a peak here, all the way up. This is 2, this is 3, to over 3 kilohertz. Now, somebody may not be actually that short, but that length is going to change where this peak is. Here's just another mathematical and physical model of it. And if that length is changing where the frequency is, and if your brain is expecting that your ear canal is going to be amplifying things at certain frequencies because of the length that you happen to have, as you move that IEM in and out, it's actually going to cause the resonance to happen at a different place. Not where your eardrum and brain is expecting it, but somewhere else. That then is going to clearly alter the timbre of the frequency response of that IEM that you're listening to. One of the things that we can see from these models here is really the shape of the ear canal and really how the tips try to work with that. So here we have 2 different copies of my ear. And even just looking inside here, you can see that that's not a circle in terms of what's going through there. Look at it from the back, you can see that is really, it's sort of almost D-shaped. That's clearly not actually a circle. You can also, of course, see the things that you've seen in your own ear, that clear shape. So let's take, say, a medium ear tip. I've got a small, medium, and large here from the same exact set. Let me get this in here. And now what you can see is that it's trying to conform to that shape. So you're not just putting it into a circle here, and that ear tip has to be able to conform to it. And where it's going to conform is, of course, going to depend on how deep it's getting inside there. This medium one, kind of take note of this distance right here. I don't know, it's probably about 8-9 millimeters or so there. But we can take a look at that. We can also take a look on the back here and see things like, yeah, it's not heading straight into the ear canal itself. You can kind of see that it's pointing off to one direction. Okay, so that's the medium ear tip. Let's go and see what a large one looks like in my ear. So this is the same print, putting out here now. Well, now you can start to see, for one thing, I've already even started folding over there. That's not going to be right. So let's try this in here a little bit more. There we go. So now one thing you can see is it's far, far further out on this. It's nowhere as far in. And you can see as it's trying to conform there and get through. And again, you can see it's really aiming off into the side of the canal. We could take the small one and put it in and see how well that actually gets in here. The small, again, you see it's conforming, and you can see it's clearly several millimeters further in than the medium or the large. So in all of that, we're getting that kind of aspect. We can again see that it's kind of shooting off into the side a little bit there. But there's one other thing I wanted to point out when looking at this. As it's trying to do this, you may say, oh, look, my ear isn't particularly small. Well, the size of your outer ear really has nothing to do with any of this. It's the size and shape of the inner ear that's going to determine how well different nozzle sizes can actually fit in here. You can see these are formed by Truth Ear Hexa, and you can see that, all right, the outer portion of the tip here is banging into the nozzle. There's a lot of room over in this direction, but no room left over in here. So with that, we're clearly getting the potential for starting to have this nozzle be too big inside of my ear. Here we've got 3 different ears. We've got my ear again over on the right here. We have my esteemed listening colleague on the left. This is somebody who we swap notes on a lot of different headphones and a lot of different IEMs. And an interesting thing is we agree very much in terms of how headphones sound. We disagree pretty seriously in terms of how different IEMs sound. And we have this ear over here who actually belongs to a famous YouTuber in the audio industry here. So, but to give you a little idea again on exactly some of the differences in all of this, we take a look at the back end of these two. You can see on mine, coming through almost straight. There's a straight on shot, angle ever so slightly. You can then see very nicely through my ear canal. Take a look at the top here to give an idea as the kind of angle I only need on that. Here's my esteemed listening colleagues. We're straight on. we have to get way down to over here. You can even see the incredible harsh angle that this is taking here as it cuts up. That angle is going to get it so that any sort of ear tip that we put inside of here is going to have to be able to tip itself up pretty steeply to be able to accommodate that. And of course, physically, it's going to have to get into this bowl while still being able to do that. Let's take a look at this ear. This ear over here now, well, yeah, you can see it's a pretty straight through shot. I mean, look at that. You can see on the top, I am perpendicular here. That's a nice thing. Straight through. But now if we take a look at the actual geometry, this is an incredibly deep bowl. We can see how far my finger gets inside of here versus how far it gets inside of here. Very, very different geometry and everything on this to be able to pull that kind of thing off. So for an IEM to fit inside this ear, it's going to have to get this past this part deep inside of there and then manage to go straight, whereas to get inside of this one is nowhere near as deep a bowl, but it's going to have to angle up pretty steeply. IEMs and their ear tips have to contend with all of this. So let's take my hexa, put a small ear tip on here, and we can see that we can get it to fit inside of my ear just fine. Works well there. If we take it on over to my most esteemed listening colleague's ear, we can say, all right, let's see if we can get it inside this here. We can get it in all right, just fine. You can see here, again, it's really pointing straight though, not straight down the canal, but into then the edge. But if we take that famous YouTuber's ear and we try to get it in here, I honestly have no idea how this person gets any sort of IEM into the ear. That's not remotely sealed, that's aiming straight down. And that's going to be a tough day. That's not remotely getting inside of here. So that physical shape is going to matter a ton. We can look at this in 3D here as well on the MRI scans that were actually used to generate those 3D models. So here, those 3D prints, here you can see I've placed a little three-dimensional crosshair on my ear, roughly where the nozzle is going to end up being. And what we can see at that point is if we take a look in, this is called the axial view. So this is as if we were sort of looking down from on top and looking at a slice of my brain. You can see where, right over here is where the shell and the body and everything would be, and the nozzle is coming in here. Now, depending on exactly how deep this is going in, it may have to contend with this bend that we're having. But some of this is also probably why you can see if you put a nozzle aiming this way, it's going to be shooting straight into this wall. And the deeper I go in, the more it's going to have to contend with that bend. Now, looking at some of the other views here, like in this view, this is called the coronal view, we can see it's a nice sort of straight shot from this point. Again, here's where this would be, and at least in this axis, it's a pretty nice straight shot. So it's not too bad to actually deal with. But you can see here, and this is called the sagittal view, that it's going to have to conform to this somewhat odd shape. Now, if we take a look at my listening colleague, again, we've placed the three-dimensional crosshair right about roughly where that nozzle is going to end up having to live. And here you can then see, let's take a look again at this axial view. You can see that right here, if this is coming in, we're starting to bang into this turn that's happening, where it's now bending back toward the back of the head here. It's going to have to be starting to contend with that. And if we take a look at the coronal, we can again see if here's where the nozzle is going to be, that tip is going to have to deal with shooting straight up pretty hard and pretty fast. This person actually uses spin fits and likes them a whole bunch. Again, as we're taking a look at trying to say exactly what the shape is it's going to have to conform to, it's going to have to conform to this complex shape if it actually wants to be able to seal. So there you have it. At least it gives you a little bit of an idea about the complex geometry inside of your ear and your ear canal, and the really, really tough job that these ear tips are trying to do to try to seal that. And then also how it is that these different tips that maybe you just thought of was trying to, give you some kind of seal, how it is that these tips can actually be impacting the sound.